Hello everyone, this is a video tutorial on solution of a problem that is related to a string and interatomic bond. So here is the question. 1 mole of magnesium has mass 24 gram and its density is 1.74 gram per centimeter cube. The center to center distance between the atoms is 2.84 × 10⁻⁻10 meter. Thin bar of magnesium 2.5 meter long with a cross section of a square that is 0.12 centimeter on the side is hung from the ceiling. 34 kg mass is hung from the bottom of the rod, that is the string of magnesium, and the elongation is observed to be 1.45 cm. So what we need to find is the spring stiffness of entire wire, the stiffness of one interatomic bond of magnesium, and how many side-by-side atomic bonds are in the wire. So firstly we calculate by finding the force that is generated by the hanging body, and where mass is 34 kg and small z is 9.8, and doing that we get 33.2 Newton. We have already given the elongation, which is 1.45 centimeter, and changing that to meter we get 0.0145 meters. Now we calculate the stiffness of the bar, so that is given by force by the elongation, and that is calculated to be 2.3 × 10⁴ Newton per meter. Now since we are finding the number of atoms in one layer of cross section, we need to find the value that is generated by the division of area of bar by area of one atom of magnesium. Doing that we can get the total number of atoms that are found in one layer of a cross section. So after finding that, we can find number of bonds that are along the length. To do that, we just calculate the total length of the bar divided by the length of one atom, and that is calculated to be 8.88 × 10⁹. Now the applied force is divided among all the atoms in the cross section and all bonds along the length. Hence the force is experienced by an atom in a layer is given by total force divided by bonds times atoms. So calculating that, we get 2.1 × 10⁻⁻20, and that is the force that is experienced by each atom in a cross section. Now we can calculate the strain, which is delta L by L on the bar, and that is given by the elongation, which is 0.0145, and the total length, which is 2.5 meters, and doing that we get 0.0058. Now the strain also applies for a single atom, so the same value is applied to a single atom. For the bond extension delta L, we have the length of the single bond times the strain, and doing that we can get the elongation, and the elongation that we get by doing this is 1.6472 times 10⁻⁻12 meter. Now we have already got the bond extension and we have the stiffness, so now we can get the bond stiffness that is given by force on a single atom by bond extension. So the force on a single atom, as we calculated before, was 2.1 × 10⁻⁻21, and bond extension, which we calculated recently, is 1.6472 times 10⁻⁻12, and that gives us 1.29 × 10⁻⁻3 Newton per meter of stiffness of a single bond stiffness, to be pretty accurate. And that solves the question.